Hello, thank you for joining us today for the first webinar in our machine learning series, Neural Networks in the Wolfram Language. We're so pleased to welcome today's presenters, Sebastian Bodenstein and Taliesin Bainin from our Advanced Research Group. Sebastian and Tali have been leaders in developing the neural net framework in the Wolfram language since the release of version 11. Sebastian will give us an introduction to the neural nets, showing how to build a neural net model and how to scale models for training on large data sets. Today's presentations will demonstrate higher order neural network programming in Wolfram language 11.3 with ready-to-use models from the Wolfram Neural Net repository. During the webinar, we'll share many online resources and links with you, and before we close, Tali will provide a sneak peek at future directions. My name is Cassidy Hinkle, Project Manager with Wolfram Research, and I will be your online host for this machine learning webinar series. I am joined by several of my Wolfram colleagues behind the scenes to respond to your typed questions during the webinar and help point you to the resources you need. Feel free to submit your questions using the control panel on the right side of your screen. You can resize the windows to customize your webinar experience. We've had good success with Firefox and Chrome browsers, so if you do experience any issues with screen or audio streaming, you might want to try logging in with a different browser. Today's webinar is a great opportunity for you to learn more about deep learning approaches to solving problems. The presentation notebooks will be made available to you to download, and they can be resources for you to use as you start working with and training neural networks in the Wolfram language. We will post links to the presentation materials in the chat pane shortly, but I want to advise you to wait to evaluate these notebooks until after the webinar, as some neural net models take time to build and might distract you from the live presentations. Before passing the microphone to Sebastian, I'm going to share a quick poll question asking about your motivation for participating in today's webinar. When the poll question appears on your screen, please select your response and we'll share the answers after everyone has a chance to respond. Thanks again for joining us. Our first presentation is coming up next.
Great. Okay, so this is the first of I think it's a 3-part series. So this will basically be an introduction to our framework. It will motivate why neural networks are interesting. And it will also leave quite a bit of time for questions where we can focus on other things, on what people actually want to hear about. So roughly, we're going to spend a little bit of time just looking at sort of what the industry is looking like for neural networks, like what applications are there out there, why are they interesting, why should people care about them, and then have a simple introduction of what are neural networks. So we're going to assume that people here have not necessarily heard about neural networks, so this might be a bit boring for people that have used TensorFlow and whatnot. And then we're going to show a full example of training a handwriting classifier, a digital classifier. And that will show off all the different pieces that you've learned. And this really is, it will be the foundation of all the different pieces that you need to understand properly in order to do your own sort of work in neural networks. And the principles are very simple. So we're going to flesh this out a bit and take this a bit slowly. And then the final thing is that Tali is going to present the future of the Wolfram language neural network framework. So kind of where we're going, basically, which is probably of interest as well for people that use other frameworks. Okay, cool. And then there'll be lots of question time, and we can focus on something else. So some of the things that were mentioned in the beginning, we might not actually cover. I decided that it would be better to focus on just the simple things first, so that for the next talks, everyone is fully on board with what's happening. Okay, and the next talks are going to be things like audio processing with neural networks and image processing, et cetera, et cetera. So those will specialize and focus a lot more on specific application domains and go in a lot more detail for how to deal with those sorts of domains. Okay, so there's a prelude to this whole thing. So deep learning and neural networks, or at least neural networks are an idea that go back to the 60s about. Lots of the main ideas were developed in the 60s and 70s, so things like backpropagation for training the networks. But they fell out of fashion for a long time. And it was really in 2012 when they came back with a vengeance. So what exactly happened? So here's a very simple problem for humans, but for programmers, it's a very hard problem. So the problem is the following. You have a set of images. So things like, different breeds of cats to different animals, kettles and pots and all kinds of things. And you have 1.5 million training images. There's like 1,000 categories of these things. And the problem is to take unseen images, ones that you've given the training images, you create some classifier or something that you want to do, and then you get to test that out on some unseen images. And the question is, how good is can you make a classifier to do that? So it turns out to be an incredibly hard problem. And there's this very famous data set called ImageNet, which is exactly this. So there's 1,000 categories, there's 1.5 million training images, oopsie. And then the ImageNet organizers, they have some unseen test images that the competitors to this competition that happens once a year, they never get to see. They just get to submit the algorithm and then it gets automatically graded. So this competition ran for a number of years, from like 2010. And the sort of approaches that people used, there was all kinds of approaches, and we'll look at some of them now. But basically, this is the sort of error rate that people were getting. So even the best methods were getting always above 25%. So even 2011, the best method was roughly about 25%. And in 2012, there was a group led by Jeffrey Hinton and Alex Krzyzewski that basically were the first group to use neural networks on this competition. And they had something like a 15-layer network, and this thing they used GPUs to train. So it's a massive data set, and previously neural networks were just too slow to train on something as big as this, especially ones with lots of layers. So they were able to train this massive net, and this was their result. They had something like 17 or 15% error rate, and the entire rest of the field are these little dots over here. So they had suddenly a completely different, and you can see how clustered the top results are all here. So the previous methods, there were variations on a theme, but really this method was completely different, and it destroyed the rest of the competition. And what's happened since then is that every year these neural networks have gotten better and better. So basically, almost all competitors started using neural networks in these years over here. So yeah, by 2017, the error rate was less than 5% on this data set. Okay, so this was basically the catalyst. As soon as you have a massive competition like this where you can't really cheat because the organizers have the unseen data, then the entire research community has to basically pay massive attention to this, and that's what they did. So immediately after, so the sort of non-deep learning approaches with things like careful feature engineering. So you basically want to find some sort of feature of the image that you can feed to things like support vector machines. And yeah, these are things that basically maxed out at like 25% error rate. Whilst deep learning approach, it uses the pixels directly. There's zero feature engineering. So it frees the researchers to look for better networks that are generally good, but they don't have to spend all their time trying to find better features. And these are very complicated things that require massive engineering effort. But also, yeah, it lets the entire system is able to learn end to end. Like in this case, the features that you're getting, there's other principles involved in sort of deciding on what a good feature might be. They're not learned together with the actual problem that you're trying to learn. They're just general descriptors that you try and construct. So the neural network approach was revolutionary in that as well, in that it freed people from having to do this sort of engineering. And it basically, every piece of the problem gets to be optimized in the optimization procedure, which is one of the reasons why you get amazing performance. So many of these models trained on ImageNet can actually be seen. We have a unreleased neural network repository, which I'd encourage people to look at. It will be released quite soon. But you can basically get access to some of these models. For example, like this was one of the, I think, winning models from 2016, maybe. And this thing can be easily evaluated, and it correctly predicts that there's a peacock. And in Wolfram language, we have things like image identifier that are basically built on the same technology. And you can also, obviously, in Mathematica, you can click and see exactly what's inside this network, and then delve deeper as well into each of these layers. Okay, so this was the sort of main catalyst event that caused a Cambrian explosion of different networks and different tasks that these networks were suddenly put to use for. So it seems, yeah, most people in the field think that this was sort of the catalytic event. And as you can see, for example, from Google Trends, basically in 2012, it was a flat line. There was not much happening if you use the term deep learning, for example. And then after 2012, it went up dramatically, and it keeps going up. So the other thing that happened was that people realized that these neural nets, they weren't just good at classifying dogs and cats and whatnot. They were good at all kinds of domains of learning task, from language translation to speech recognition, etc. So I'm just going to have a look at a few of these quickly, because it's interesting to know roughly, what can these things do? Just to have an idea of where this field is currently at. And I don't want people to leave with the idea that all that these networks can do is something like classify images. That's absolutely not the case. They are used in a wide variety of things. So for example, Google Translate, they switched to using neural nets in 2016. They had a different kind of system before that, and it had major performance improvements. So from a New York Times article, as dawn broke over Tokyo, Google Translate was the #1 trend on Japanese Twitter, just above some cult anime series and a long-awaited new single from a girl idol supergroup. Everyone wondered, how had Google Translate become so uncannily artful? And you can actually use this in Mathematica as well by just using text translation. And this calls the Google Neural Translation API. Is this running? Oops. This was working. Oh, okay, there we go. Okay, so other things. Autonomous vehicles. So one of the hottest sort of things at the moment is self-driving cars and the sort of massive rush for all the different companies like Uber and Waymo and whatnot to construct the first commercially available autonomous vehicle. And one of the key components of these vehicles is our neural networks. So the neural networks do all kinds of image processing. So we actually have one of them in the neural network repository. You can click on this link. I didn't actually put the code in here because it requires a bit of extra pre-processing code that is a bit ugly. But you can look at this link to actually see the full thing. But basically, and run it in Mathematica, sorry. But the basic idea is that, for example, you can take a scene and the neural network can tell you, okay, these pixels here correspond to people. So it sees that there are people walking around, exactly where they are, where their legs are, et cetera, et cetera. And it can obviously say, there's other pieces here that are the roads, the sky is up here, there's some buildings, et cetera, et cetera. So basically, neural networks are used to get an idea of the world around the car. Other things, so things like speech recognition. So basically, all the modern speech recognition systems that you might find on your phone or anywhere else will use deep learning now. So we actually have an example of that in the repository, which again, you can click on, which is a very good speech recognition system trained by Baidu on about 8,000 hours of English. To other things like question answering. So we have a new function in 11.3 called find textual answer. And this was trained with the Wolfram neural network framework. And there's a nice blog post that you guys can look at from Jerome from our group about exactly how that was done. So yeah, I mean, here's a simple example. You can give it a question, and there's some big paragraph of stuff. And the question is, let's see if this works. So this thing, if you use this yourself, it'll be downloading the network that actually does all of the stuff. What happened there? Okay, there we go. So it correctly extracted that it's 1 meter, the size of the dodo, from this text. And basically, for this sort of task, every method is a neural network method. So it's basically the only game in town for this sort of thing. Okay, so rapidly on to other things like reinforcement learning. So AlphaGo, people might have heard of this. So Go was a game that was generally considered an almost unsolvable game, and at least a decade away for having any sort of reasonable solution. And DeepMind shocked the community by releasing a Go player that beat one of the previous world champions, Lee Sedol. And there's also, quickly after that, there's a new version of this called AlphaGo 0, which completely learns from scratch, and it's a lot better than even AlphaGo. So this, one of the key components was a neural net. So it's other random things. So things that you might not even think are really learning tasks. So things like restyling images. So I might say, here's a content image, I want to restyle that into the style of this thing, for example. So I can run this. And here's the resulting image. And you can do this with, all kinds of different images. And this is the foundation of image restyle, which is also a newish function in Mathematica. So one of the trends that I want you to see is that for internal functionality, we are using our own framework to do all of these things, like image restyle and the question answering to all kinds of other things that are coming up, from speech recognition to translation. So this framework it has to be powerful enough for us to actually train these things ourselves. And so users basically get a very good framework. Okay, another random example is, let's say, colorization. So in this case, you want to say, here's a black and white image. Please colorize that or reconstruct what a plausible color scheme looks like for that. So we can try this, and there's the new image. So the network obviously has to recognize, this is grass, this is probably a dog, and dogs come in certain colors when they look like this, etc., etc. Okay, so it could go on and on. There's a lot of things that these things can do, from reconstructing 3D faces, from 2D faces, to geolocating an image based on just the image and a massive training set that they were trained on, to all kinds of other things like medical imaging. Even I think yesterday was the FDA. Well, I think it's the FDA. What is the medical organization in the US? They approved a diabetic retinopathy detector that's based on deep learning for medical use. So medical imaging is a massive, massive field. There's all kinds of NLP stuff, natural language processing, from sentiment analysis to all kinds of other things. So you should already go to the site, and you can find a bunch of other things of networks that are currently runnable in Mathematica. Okay, so now that we've seen and hopefully motivated somewhat why people should be interested in this sort of thing, that they can be applied to all these different problem domains that previously didn't have really good solutions. So what are neural networks? So let's spend a bit of time thinking about this question. So the modern term for neural network is actually differentiable programming. And we'll see why that is quite soon. And also, just that people know, there's a very nice introduction to neural nets tutorial in the Mathematica documentation. There's a link for that there. And some of it is based on that. Okay, so the very most basic building block of a neural network is a layer. So, and other frameworks might call this an operator. So a layer and operator, it's some basic piece of computation that acts on numeric tensors. So let's have a very simple example here. So there's something called element-wise layer, which allows you to have layers for all sorts of element-wise functions like tan h and clip and all kinds of things of that sort. So one thing is, a sort of property of these things is that they can only act on numeric tensors. So here's an example. So element-wise layer, we can apply this to some input. And this is the same as in top level if we said, and they're both the same result. So here's where the differentiable programming idea comes in. So the idea is that you want to have layers that are differentiable. And the reason for that is going to be for being able to optimize and learn what the parameters are in these networks efficiently. So the idea is that if every piece is differentiable, then if you stick them all together, it'll remain differentiable and it'll be very efficient to optimize. So there's a way of differentiating these layers with net port gradient. So you can say, give it some data and you say, I want to get the gradient of the port input. And what is a port? Well, these layers, if you click on it, you can expand it. It says there's a number of ports. So there's an input port and an output port. And the reason for this is that you want some way of being able to specify unambiguously, if you want to connect up, let's say, the output of this thing to something else. In this case, it's trivial. There's just one input and output. But for many layers, they can have multiple inputs or multiple outputs. So you can specify in this case explicitly, like I want the gradient for the input port. So we can do that. And that's exactly equivalent to just differentiating symbolically, and then in this case, just replacing that symbolic variable with some inputs. And what this is really, okay, so there's some other properties that these layers have. So one difference between these layers and other Mathematica functions is that they can operate transparently on GPUs. So it's become imperative to train on GPUs, like CPUs are just too slow. So this can be either CPU or GPU, for example. And you can also, if you have multiple GPUs, you can specify potentially which GPU you want to run this thing on. Like if I had 4 GPUs, then I could do something like that, or 3 GPUs. Okay, so everything works on GPU. So any combination of these things will also work on GPU. Then some other random things. So one is that there's something, this idea of shape inference. So these layers, if you tell it what the input size is going to be, so I'm telling it that in this case it's a matrix of 4 rows and 32 columns, then it will automatically infer what the output shape is going to be. And we'll see a bit later why this is important and useful. Okay, so one of the most important differences, though, between just normal functions in Mathematica and layers is that layers can have learnable parameters. So if this was all that it was doing, so like just, oh, here's another version of tan h or whatever, like there's no way that this thing can learn anything because you just, it's just a function that you're constructing explicitly. But the magic happens when you have learnable parameters. So layers that have learnable parameters, they will often look like this. There'll be something uninitialized. If you click on it, there's the ports, the input and the output. And again, they've got, if I told it what the input was, and I tell it that this thing has, it's a 3-layer net, or sorry, with 3 neurons, let's say, then it knows exactly what the output is going to be. But it also has these parameters here, weights and biases. So these are things that you want to learn, and they can adapt based on the data. So in the beginning, they don't have any values, right? They're not defined. And if you try to extract the values, then it'll just say automatic. But there's a function called net initialize, which allows you to initialize these weights and biases to some random values. And that's the general philosophy with neural networks, is that before training, you need to randomly initialize them to something that's not 0, like the weights. If everything is 0, then it has huge difficulties learning. And there's a very complicated procedure for deciding on what the scale of the random data should be that you're initializing these things to. And all of this sort of thing, our framework completely automates. So there's no decisions you need to make. Okay, and then now you can say net extract, and I want to have this dot layer here. I've initialized it, so if I look at the weights, there's actually are some weights now. And I could do the same with biases. Okay, and obviously it goes without saying that I could now evaluate this thing as well. So if, oh, oopsie. So if I was to say dot 2 of, let's say 1, this thing takes a vector of size 2, it'll now evaluate. But dot 1, if I try to evaluate this thing on that, it'll say cannot evaluate net because I haven't specified the value for the weights. Okay, so all of these examples so far are things with one input port. So one classic example of something that has multiple input ports is a loss function. So a loss function is something very simple. It basically takes an input and a target, and it tries to have a high number. So it's always a one number loss function, and it tries to have a very low number if the target and the input are very similar, and it has a very high number if they're very far apart. In this case, it's basically the Euclidean distance between two vectors, for example, if these were vectors that I would be putting in. So here's a very simple example. So I have an input and a target, they're quite different. If I make the target, this is 4 and this is 1, if I make this 99, this number goes up. But if I made this 1, this number is now smaller. So this number gives the network an idea of how close it is to the truth. And this is the key part that is used for training the network. Oh, sorry, okay, is it a bit wider? Okay, make it wider. It's not getting... Okay, is that better? Okay, I think that's wider. Cool. Sorry about that. Okay, so there's also, you can list what layers are actually available to you in the system. And each of these obviously has a lot of documentation, and they all have different sort of behavior. So some of them are just, very similar to what Mathematica would do. So things like append layer, it does basically the same thing as append. Or like dot plus or dot layer, it does the same thing as Mathematica dot. But then there's a whole bunch of layers that have no analogs in top-level Mathematica. So things like instance normalization layer, which does some sort of normalization of the data, or spatial transformation layer and whatnot. Okay, and this is like becoming proficient in using neural networks involves understanding what all these different layers do and when they're appropriate to use. And that's going to be probably a larger topic that will be carried on for the next, I think, sessions. Okay, so at least one of them. What does the linear layer do, at least? So this is the simplest learnable layer. And this is sort of also one of the oldest layer types. And I must mention that these layers, they keep growing. One of the reasons is that people invent new layers all the time. And as they invent them, we want to implement them and have them in our framework. Okay, so the simplest learnable layer is just a linear layer. So the Mathematica equivalent of that will be this. You just dot producting the weight and the data, and then you're adding some bias term. So the data is some sort of vector, and the weight is a matrix. So basically what this layer is doing, and we can just verify that it is actually the same. We can extract the actual weights. Oh dear, what's going on there? Oh, I didn't, sorry. Initialize that, there we go. Okay, so all that this is doing, like the linear layer, it's often called a fully connected layer because you could interpret, there's let's say an input vector of length 3, so 1, 2, 3. So this is what this input here might look like, and there's basically the matrix can be that you've got the weight matrix can be interpreted as sort of new connections between this neuron and the neurons of the output, and there's a weight per connection. So that weight matrix basically represents that. And all that it is a linear transformation of the data. And linear transformations, they can have things like They can rotate the vector, they can rescale it, they can shift it a bit, etc., etc. So whatever linear transformation can do, this layer can learn to do that thing if it's good for producing the predicted result. Okay, but this is a big topic, and things like what do convolution layers do, and what do pooling layers do, etc., or recurrent layers. These are going to be topics that will be very deeply explored, I think, in the next talks. So I'm not going to go into that too much. Okay, so layers, I think we've understood now, right? So layers, they act on numeric tensors, and they have a whole bunch of properties, like they're differentiable, and they work on all different devices, etc., etc. But layers themselves are not very useful. Like just that linear layer, it can't really learn much. And in fact, one linear layer is the same as logistic regression if you were to do a classification problem and try and solve it with a single hidden layer network. Or linear regression as if you try and, if you're predicting a numerical value with a single linear layer. So, and those are very weak sort of learning systems. So one of the main ideas of neural networks, or deep learning, I guess, is that you want to have a long set of transformations, a deep set of transformations that allow much more complicated behavior to be learned than just single layers. So the first container type is a chain. So this is very simple. So a chain is simply a linear, it's a sequence of operations. So a linear sequence. So it has one input. We can try this out. So if we look at this thing here, so this thing has one input, it has one output, and it just is doing first the 10H, and then it's doing the logistic sigmoid on the data. And this is exactly the same as this, for example, in top level. And you can also verify that they're the same. Okay, this is a bit of a silly example because you could, in this case, it would also be equivalent. So element-wise layer is a very powerful layer. It can have, for example, something like this. So logistic sigmoid takes in that, and that takes in, and that's a perfectly valid layer. You can compose all the different primitives that an element-wise layer has, and you can make a pure function, and that's a perfectly valid element-wise layer. So this will be the better way of writing this thing. But this is just to show that what this actually does. Okay, so a lot of networks, and traditionally almost all the networks have been just chains. So yeah, the sort of traditional image classification networks, even the one that won ImageNet, they can all be represented by this chain construct. That's all they need. However, what happened after the 2012 ImageNet result was that people realized that there's a lot of power in having actual or more complicated sort of structures that you can have. And one of them is the graph. So a very simple graph would be something like this. You have two different inputs, and these inputs, the first input goes into tan H, the second one goes into logistic sigmoid, and then they get added up together and then returned. So this graph, the idea is that you can, the first sort of list here, and this can be a list or an association. So if it's a list, it means you basically, you have all the layers that you want. And then the second argument for netgraph is a list that gives the connectivity structure. So just exactly like graph, how graph works. So in this case, I'm saying that the first port of the input is going to the first layer, so tan H, and the second port of the input goes to the second element in here, this one here. And then both of these go to the total layer, which totals them up. And you can do the same thing with association and then with names rather. Some people find that much easier. So tan H goes to that, and then you'd have this stuff here, for example, changing to being tan H. I personally prefer that method as well. And this must obviously be an association. And these ones must be changed to do. Okay, so the question then is, is this equivalent? What is this equivalent to? And in this case, yeah, it's just function composition like this. Okay, so you can build very complicated structures with netgraph. You can also differentiate it, because all the layers are differentiable, so will the netgraph be differentiable. And this is an important point, is that containers behave exactly like just normal layers. So they're differentiable, they're on the GPUs, but they can also be nested. So netchain expects a layer over here, but a netchain is a layer as well. So this is perfectly valid syntax. And if you dig deep into this thing, you can find the different layers of netgraph, of netchain, sorry. Okay, and obviously the models in the repository are almost all some form of container. So an example of this would be this restyling net. This thing has two different inputs, the style image and the content image, and it does some processing. And you can dig deeper and click on these things and get, see what it looks like. Okay. So containers are important for building more complicated structures. But containers and layers, they still only ever operate on numerical tensors. But what we had, what you might have noticed right in the beginning, was acting on actual images. Like we would take a net model, this thing, and it would apply directly to the image. So how does that happen? So the basic idea is that we have another construct, and this construct is quite different from anything that we've seen in other frameworks. So the construct is the idea of a net encoder. So net encoders are special, almost like a layer, but they can't go inside the net graph or net chain, or they're not real there. They're not differentiable. They don't work on all the devices, etc., etc. But they can be attached to the inputs of other layers, which we'll see now. So basically, what they do is they take some type, so like an image or an audio object or text, or any of the other types that you might want to operate on with neural networks, and it basically produces the appropriate tensor from that thing. And you can see from this, so this says, okay, it must be a grayscale image. It has one color channel. There's no mean or variance images that you could set as well. And it's got an output shape of this. So if you give it an image, it produces this tensor. So it makes a guarantee that the tensor that this thing outputs is a 1 by 12 by 12 tensor. And if this image was much bigger, it would just reshape it. If it was a different color space, it would conform it. So it can basically guarantee to the network, this is the kind of tensor that you'll be getting. And another cool thing that you can do with this sort of thing, with the encoder, is that it can operate directly on files as well. So if I have a file for some image, then it can directly run this and give you a tensor. And this should be 1 by 12 by 12. Oopsie, sorry. 1 by 12 by 12. Great. And the reason why this is powerful is that you can do out-of-core learning for images and audio files with this, because you just have to, you can use the file as an actual data point to feed to the training, for example. So you don't actually have to load all the files into memory. You can just have them on disk and then just give the file names, and then NetTrain can act directly on them, or the networks can act directly on just the file paths. So file paths are completely valid inputs to these encoders. And if you're more interested in, I was going to touch more on this later, but I decided to simplify things. So if you are interested in training on large data sets, then there's a tutorial on doing this. Okay, which I recommend you looking. And so there's a whole bunch of other encoders, from audio to characters to for tokens to, you can write your own custom encoder as well. So it depends on what data type that you're dealing with. Okay, and as I mentioned, the main sort of property of these things is that, remember the input port. So you can specify what the size is for the input port, but instead of doing that, you can attach an encoder to it. And if I do that, instead of saying what the size is, it will tell you that the input is an image in this case. And what this means is that you can act directly. So this case is a pooling layer. You can act directly on an image. If you try to do that without this, it'll just complain because it's not a type that it accepts. So if we did this pooling layer and we said, let's give it some image, data supplied to port input was not a tensor of rank greater than 1. Okay, and one more thing. If you remember the networks that we showed right in the beginning, for ImageNet, these things had the magical property that here's the net chain. They could be directly applied to the image. Just give it to the, give the image to the network. And the reason for that is that it has this image encoder on top. And you can always extract the image encoder. You can say net extract of the input, and you can see what this image encoder is doing. It's resizing them to 299 by 299. It has some mean images, some mean image. It has, and it's RGB color space. So that's why this network just works out of the box. So for other frameworks, you often have extra pre-processing code that would have to conform the image into the size that the network requires. Okay. The basic, almost brother of the analog of the net encoder is for the input is that there's going to be a net decoder for the output. And the reason for this is very simple. It's that for a lot of networks, for example, like classification tasks, you really want, the network is always going to give you back a numeric tensor, but that's not really what you want. You want some sort of class. You want to say, is this a dog or a cat, for example? So what this does is that if you create this decoder, you say it's a class decoder, and there's two classes, there's a dog and a cat. If I give it a probability vector, it will then interpret, it'll take the maximum probability, which is 0.9, and say this was a cat, because that's the one that corresponds to 0.9. And you can use this exactly like a classify function, which is that you can ask for different properties here, like what are the probabilities? And it'll give you an association with the probabilities for each of the things. And exactly the same analog, if you have this, you can attach this to the output port of a network. And this is, you can see now why these ports also need names. Like you need ways of referring to them. So like if there were multiple outputs for something, how do I specify which output to attach some decoder to, for example? Okay, in this case, there's a softmax layer, which basically just produces, it takes a random vector and it produces a normalized vector, so that sums to 1. If we apply this, now softmax directly works on, it directly produces something like this, which is definitely not just a numeric array. Okay. So the same thing happens with these networks. So things like this ImageNet network, it has a whole bunch of classes, and if you click on this thing, you'll see that the output has a class attached to it, which we could extract. And if we run this network, it means instead of giving you, just a big splurge of probabilities, like there's a vector of size 1001 in this case, you can actually get the real class from that. And you can, obviously, if you want the probabilities, you can ask for them here as well, but this might take some time. Okay, and you can get the output decoder in this case, and you can get the class labels and all that sort of thing out if you really want. Okay, so I hope that people can see sort of what the motivation of this thing is, that it makes the networks very clean. Like this is ready to go, this network. It doesn't require lots of post-processing scripts and whatnot. So, okay, so now that we've discussed the main sort of concepts, so there was decoders, encoders, containers, and layers. So now we actually want to train something. So that these networks are not very interesting unless you can actually do some, that it can do some learning. So how do we do this? Well, there's a whole bunch of automation that's introduced by the framework, but I'm going to show you some examples where I don't make use of this automation and just do it very explicitly that you can see exactly what's going on. So here's a very simple example. We have some data, which is pretty much a straight line. 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. And here's a very simple net that we want to have to solve this problem. So in this case, we're predicting one number, a vector of size 1. And here's where the magic happens. So we have an input. It comes in, it goes through the linear layer, and this has parameters. And we want to find the parameters so that the prediction of this linear layer is the same as the target prediction, so that the mean squared loss layer becomes very small. So if we do it right now, we've initialized this network. This is random initialization. This is pretty big. So obviously that's what we expect, because these parameters haven't seen any of the data. They're just randomly picked. So currently the predictions of the network of this linear layer don't match at all what the target looks like. Okay, so now we can actually train it. And there's a very simple construct called nettrain. So nettrain takes a network, and it takes some data, the training data, and it will train. So that happened very quickly. We can do it again. So basically, this tells you here what the output looks like as a function of training iterations. So it does many iterations, and you hope that thing goes down, because you want the loss to get smaller, which means that your predictions and your target match. And now we can check exactly the same thing, which previously we had 15.31. If we run this now with a trained network, we get something like that. So this network now has learned to predict what the target looks like. Okay, and we can also extract the parameters. We had a net with some weights, and we have a new network, the trained network. And we can see what the weights look like. So for the trained net, the weights are completely different. And that's the whole point of training, that it can change the parameters. Okay, and just a quick rough idea of how this works. It uses something called gradient descent. And this is where the differentiability comes in and where it's so important. So the basic idea is, suppose this J here is the loss. So it's a function of the weights of the network, right? Or the parameters of the network. So we want to find, so for different parameters that you have, this loss is going to be different values. And as we saw, so there's going to be a point, though, where there's going to be a minimum. And in fact, there's multiple minimas. So there's a whole landscape of minima. But the basic idea is that if you're a blob and if you're sitting over here in parameter space, so if your parameter puts you over here, then if you have the gradient gives you an idea of the direction that you must go so that you get more closer to the minimum. And that's what nettrain basically does. It uses the differentiability of the net, and it moves you in the direction where you need to go. Okay, so this is also very similar, people might realize, to things like n-minimize or find minima, except that it's vastly more efficient for various reasons. Okay, so that's the basic idea of the training, and you don't have to worry it's good to know what it's doing, but nettrain does automate a lot of that stuff for you. So now that we have this background, let us actually look at a real sort of example. And this is often considered a toy example, but it is the simplest toy, maybe the least trivial toy example that you can have that actually does something nice. So we get the data, and we can look at some examples, and probably most of you have seen this sort of thing. And one of the reasons for using this example as a starting point is that a lot of people have seen it, and it's familiar, the problem that is involved with this. So the problem is very simple. You have some handwritten digits, and you have the actual label. And so you want to predict for unseen images. You want to learn how to predict the correct label for those. So what have we learned? Well, the first thing, obviously, and this is something that I think that the next speakers will emphasize a lot, but basically, it's very seldom where you will be actually putting together very complicated nets from scratch. with lots and lots of layers. So the most common thing is, the neural network community has spent a lot of money and time looking for good architectures for doing certain problems. So your first instinct should always be to say, let's go to the neural network repository and find something that does something similar to what we're doing. If it's image classification, there's a whole bunch of incredible networks that have won on ImageNet that will be a very good fit for what you're doing. And it's unlikely that you'll ever find a better architecture. So this should be your first instinct, almost always. Find an existing network for a certain task. And one other reason why it's very nice to use the repository is that you are guaranteed that the implementation was correct. It's very easy to see a paper and then make mistakes with these numbers. Like, this is a very small net. You're probably not going to make mistakes. But for some of the networks that have 500 or 1,000 layers, it's very easy to make small mistakes, and then the whole network doesn't work properly. So yeah, so this should be your first instinct. And in fact, for this particular task, there's a very famous network that we have called LINET, which at some point supposedly sorted about 10% of America's checks. This was like in the early 90s. Jan LeCun worked for, I think, Bell Labs, and they made one of the first sort of industrial grade neural network recognition machines for check digit recognition. So it has a very pristine history, or prestigious history. So this network does exactly what we want. It's a very simple network. It has convolution layers and pooling, and this is something that for the image talk, I'm pretty sure they'll explain carefully what these layers do and why they're special and why they're used for images. But yeah, so you could run this model immediately and you'll see that it works. But let's do this from scratch. So using all the different things we learned. And I also want to say, if you want to see the most efficient way, or the fastest way of doing this sort of task, there's a tutorial for MNIST digital classification, and it's very, very short. It's a very, very simple few lines of code to actually do this the simplest way. But the simplest way is not the most general way. So the simplest way works for problems where there's basically one prediction, where there's one input, but it doesn't work for anything else. So we're going to show for this basically the general approach that'll work for any sort of problem, even though it makes, for this very, very simple problem, it makes it look a lot harder than it is. Okay, so the first thing that we want is we want a decoder, because we want this thing to predict the classes, and the classes are going to be between 0 and 9, because the digits are between that. And we also want an encoder, which takes an image, and it makes sure that it's 28 by 28, the size, and they're going to be grayscale. Okay, so the next thing is to actually define this convolutional network. So I'm not going to explain all that carefully about what the motivation is for each of these things. Maybe the only thing I'll mention is that convolutions are usually used for structures like sound, like spectrograms or images, which are large, and you don't want blow up of your parameters. Like the fully connected layer or the linear layer gets incredibly large for images. Like if you have a 500 by 500 image and then you need a matrix that multiplies that, you just have a blow up of parameters. But there's a whole bunch of other reasons. Like there's certain symmetries that are encoded or invariances that you hard code into this here. So you say things like, for a classification problem, I don't care that the object could be anywhere in the image. I don't really care. And that's invariance to shifting the object in the image. That's one of the reasons why you have a pooling layer, for example. So you can prove that a pooling layer makes it equivariant to translations, or an object to translations in the image. And so this is sort of principle in neural networks, is that if you can encode structure, so if you know that there's some structure in your input, you want to use layers appropriate for that to exploit that structure, and it makes learning a lot more efficient. But this is a longer topic that maybe we can deal with some other time on the next version, or maybe even the questions. Okay, but basically, so there's a whole bunch of convolution layers. There's a nonlinearity called like a ramp layer, and this is a very important thing probably to know as well. So if you plotted this thing, it'll just look like, let's say, -3 to 3. And this thing it's flat, and then it goes upwards like this. This is also called ReLU layer sometimes, or rectified linear layer. And you'll see them between things like linear layers or convolutions or whatever. And they basically break the sort of linearity. Each of these operations is a linear operation. And so you have a bit of nonlinear behavior here, and that helps the network learn much better. Okay. So we've now created this thing. Now, this is where things become more complicated than they need to be for this very simple example. But I'm going to show how to do this for the general case. So here I'm actually constructing the training net. So for these simple examples, you can actually feed this straight into nettrain, and it'll construct the whole learning graph, or the training net itself, and then give you back the original network that you had. But that doesn't work for all networks, especially when there's multiple inputs or outputs. So what you can do is, in this case, here's the net. We're just having the uninitialized net, so the input goes to that. And then the input goes to loss, which we've just explicitly added here. And this will be cross-entropy loss layer. And cross-entropy loss is usually what you use for classification. So this is one of the things that you have to learn as well, like what losses are appropriate for different tasks. And this is a very good loss if you have two different probability distributions that you're comparing. Okay. And we can evaluate this in some training examples, and you'll see that it's quite large. Okay, so we have this training net, and we want to find the parameters in the net so that the prediction that it makes is similar to what the target is. And the loss gives you a number that will be small when that happens. There's one more thing, which is that this net now has two ports. It has a target port and an input port. So the most general way of representing data when there are multiple ports is the association form. So basically you have this sort of thing. So you have one port and it has a bunch of examples, and then there's another port that has a bunch of examples. So for training, this is the most general form. And some networks, they might have 5 of these ports, and so you can easily represent that data. Okay. Now let's train this thing. So this is a more complicated syntax of the previous thing that I had, but let's start this. So the first thing to note is that I'm going to use GPU. Now, not everyone can use GPU. You can only use it if you have an NVIDIA graphics card, unfortunately. So whilst it's running, we can explain what all the different things are. And sorry, also this display looks a bit strange for presentations. There's some bug. It makes it look small. Okay, so it's busy training. So let's look at all the different pieces whilst it's doing that. So there's the training net, there's the training data association, there's a validation set. Now this is very important. So when you use things like classify, there's a lot of things that are automated for you to prevent things like overfitting. So overfitting means that you do very well in your training data, but you do terribly on any other data. And there's a very good tutorial on overfitting if you're really interested in that. Called tutorial, training neural networks with rigorization. So basically this validation set, what it does, it's not allowed to use this data for training, but it checks, as you can see here. So this loss curve, the blue is the validation performance. And as you can see, it's getting better and better on the training set, but it's not getting better on the validation set. So what this will do is it'll say, okay, we can take the network that did the best on the validation set and return that to the user. So for example, this graph might look like, the validation set goes down, 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 and then suddenly it can go up again. And that's the sort of classic signature of overfitting. So in this case, it doesn't look like it's overfitted too much. It looks quite fine. But this thing, if you provided a validation set, it'll protect you quite well from any sort of overfitting, because it'll just take the point that it did the best on the validation set on, where it wasn't overfitting yet. And that's really probably the most recommended thing for people to do to save themselves from that problem. Because yeah, like NetTrain doesn't automatically, deal with overfitting like classify and predict might do. Okay, a whole bunch, some other things, like how many rounds of training. This means how many times does it go through the entire data set before it stops. And you can obviously, we can actually run this one more time. You can stop the training at any point. So if I wanted to stop it now, I could just say stop and it will return the training results for me. Okay, that was maybe not the greatest idea because I have to retrain it for a little bit at least. And yes, and this last thing was that there's an argument all here. It just means that it returns this nettrain results object. So normally if you don't give this argument, it will return the actual train network. But in this case, it gives back the train network that's in this object, but it gives back all the other training information as well. So things like what was the validation loss, et cetera, et cetera. And we'll see that now. So this is almost done. And this will take a lot longer on your CPU, unfortunately. Okay, let's stop it now. Okay, so we have this network that's been trained with the result object. So from the result object, there's a whole bunch of properties that you have. So things like you can get a nice plot of the, of the loss for training, for the training set, which is the orange, and also the blue, which is the validation set loss. And we can see that it hasn't overfitted too much because the validation set is still going down. Okay, we can also get the network out. So results train net will give you back the net graph. So what we really want though is we want the prediction network. So we want to get out, this net graph, but also inside the net graph, there's a node Linnet, which is the prediction graph. We can discard the rest of the network because we're not doing training anymore. So there's a little bit of annoyance that you have to do, which is that the encoders disappear if this thing is now, if you extract this thing, the output encoder is not there and the input encoder is not there. So you have to just put them back, which is pretty simple with net replace part. And we can now use this train net to actually make some predictions. So this is a 2, and we can get some probabilities out. It's pretty confident that this is a 3, but it's a bit unsure. And as you can see, like it's been cut out a bit. So that's pretty good that it's not 100% confident. And you can do things like obtain the accuracy of this thing, which gets about 98.6. So that's roughly, So for classification tasks, it's very simple to get metrics out because you can just use classify measurements. So if it's a classification task, it's classify measurements. And the same thing that happens with predictor if you're doing regression. Okay, and this is a duplicate, oopsie. You can do the same thing with classify as well. So you can try run classify. And you can see how much simpler classify is than this. So classify is fully automated. It does all the pre-processing. It does everything for you basically. And all of this rigmarole that we went through, you can achieve something similar with classify, except that classify has a lot of limitations. It's not as flexible. You can't do out-of-core learning, et cetera, et cetera. And obviously, if the only problem was to do simple image classification, then something like classify might be appropriate. Okay, let's just stop it. I don't have that much time. Okay, well, we didn't let it train very long, but got that. Okay, so just to summarize quickly. So I've given a very basic introduction to the framework and different pieces of it. And there's obviously, I gave lots of links to things that are more complicated. So things like out-of-core training. There's all kinds of other ways of dealing with overfitting. So things like using dropout or other kinds of regularization. So those are things that you probably have to look at yourself. Okay, and the last thing I want to leave you with before I give you to Tally is that just a quick sort of rundown of this framework. So first of all, it's an industrial strength scalable framework. We use all the latest NVIDIA libraries. We use MXNet as a backend, and we contribute to MXNet as well. So all the companies that are working on MXNet, and it's backed by a whole bunch of companies, from Amazon to Apple to others. Users automatically get all the benefits that accrue to all the things that improvements are made to MXNet. We also use this extensively in Wolfram Research. We're developing a whole bunch of functionality based on neural networks, from speech recognition to things you've already seen, like the question answering to image identify. There's image contents is coming. There's something like a list of 70 different functions that we've got that we want to make with this framework. So it's not just something that we don't use. We use it very extensively. And we also plan to have the best repository of networks, which is already, I think, a lot better than any other frameworks repository. So we're putting a lot of effort into collecting from nets from other frameworks. So we convert them for you. We convert the pre-processing into Mathematica codes if there's pre-processing involved, and all the hassle of converting. And converting is a tricky business. It's unfortunately a lot harder than it needs to be right now. So yes, and also the networks that we train ourselves are going to go onto this repository. So those hopefully 70 functions that are on our list, those nets will be available to users. So one thing I think, there have been comments about this as well. There's no lock-in. So we thought it was a very important principle to follow, that users of the framework are not forced to have their stuff only in Mathematica, because you might want to, deploy on TensorFlow serving or who knows what. Like, there's a lot of options you might have, and we definitely don't want to lock you in. So we already support import export to MXNet. I should have actually put the link for that, but you can look in the documentation for that. And we also have plans to support sort of the main candidate for a completely cross-platform format, which was started by the PyTorch and Cafe2 and Microsoft CNTK framework people. But it's now been adopted by MXNet and Chainer and a bunch of others. And we hopefully will support that as well, to both import and export to that. And we've tried to make ourselves be easier to use than other frameworks. And this is what sort of the selling point, I guess, that we want to have, is that we want to be as simple to use as possible. And for certain things you might see for the next talks, so things like true variable length sequence support, these are things that are very hard to do in other frameworks like Keras and whatnot, where you have to do your own masking and ugly things. And things like the encoders and whatnot, it just makes it very simple because everything just runs. There's no extra Python packages that you need to run to process your audio or images. Everything is just part of the language. So and this thing also, it works out of the box on all different platforms, from Raspberry Pi, where it ships with, to all the other major platforms. And also one thing I didn't mention was that we do support quite simple cloud deployment. So there's like API function and cloud deploy that allow you to deploy these networks onto the Wolfram cloud for you to make APIs with. Okay, cool. I think that's basically the end of my talk. And Tally will be with you next. So thanks a lot. So how do I stop? Sorry, I was muted. I forgot to mention that there's one last poll, and this poll is basically what users would want to see the most in the next version of Mathematica for the neural network framework. Thanks. Hi, so this is Tally. So with Sebastian, as he mentioned, I'm one of the developers of the deep learning framework in Mathematica. And I'll quickly summarize this poll, and then we will look at my section of the talk, which is kind of some of the future work that we're planning and some of the features that you can expect to see in future versions of Mathematica. One quick question, am I sharing my screen? It's hard to tell.
Not yet, Charlie. I'm going to hide the poll results and then I will hand over access to you.
Thank you. Cool. Looks like people are pretty keen on seeing a book, which is very interesting. It's certainly something that would be fun to write. Okay. Great. Can everyone see my notebook?
Yes, we can.
Great. Cool. So I want to cover four areas. I don't have much time. I've got about 10 minutes. I just want to cover 4 areas and then maybe leave it open to questions. The 4 areas we're concentrating on, you can kind of group things up into things about scalability. So that means making sure our framework can work on sort of bigger and bigger problems, on training on more devices, being friendlier to long-term training that lasts many hours or days. Then there's ergonomics, which is making it easier to use and to define networks clearly, to sort of see what's going on. Then there's flexibility, and that's making sure that we can actually represent some of the latest networks that can sometimes have more exotic kind of layers in them, or sort of funny things going on that we haven't yet. We may not have layers defined, or we may not allow you to do the kind of manipulations that you need to implement a particular technique. That's making sure that we have those things. And then the 4th area is interoperability, and that kind of really means making sure that once you've trained a network in Mathematica and the Wolfram language, you can get it out, use it in production, use it in conjunction with other tools, and the inverse of that. So like taking networks that other people have trained in other frameworks, whether it's sort of Keras or PyTorch, and getting them into Wolfram language so that you can use some of our features. So let me start with scalability. The primary thing that we're working on, and it almost shipped in 11.3, is multi-GPU support. The rough idea is that you'll just be able to specify, instead of a particular GPU, like currently you can say GPU 1 or 2 if you have multiple GPUs, you'll now be able to say GPU all. And that will mean that we will divvy up the batches into smaller batches that are given to each GPU independently, and then the gradients are synchronized using the high performance NCCL library that NVIDIA provides. This will also be possible for evaluating a net on large quantities of data, and you might want to do that to measure its accuracy or to conduct experiments of another kind. And yeah, you'll be able to make use of all of the GPUs that you have on your system. So the next feature that we'll be supporting, and again, this is very low-hanging fruit relative to the other things I'll talk about, is support for half precision and double precision types of array and computation in the framework. And what that means in practice is, for half precision, that you can train faster, and your nets will
will occupy less memory while training and also when saved to disk. And in some cases with some hardware, potentially quite big speed ups. So NVIDIA likes to talk about the tensor cores that they have on their V100s. These are available. I mean, you can buy them, of course, but you can also use them on cloud compute services like AWS. They have, I mean, reading roughly off the numbers, a factor of 10, offer a factor of 10 kind of increase in maximum throughput of floating point operations if you just give up half the precision of all the numbers you use. And it does mean that you have to use various tricks to make sure training is stable enough to be useful. So we will do these things automatically, but the payoff is potentially quite large for that. And then just because it's not that much extra work to ensure, we will also make sure that you can use double precision. That certainly can be used by less people, but it will unlock certain use cases that I think are quite interesting. The way you'll use this in practice is by providing an option called working precision, either to net train if you want to train at lower precision, or to the net when you're evaluating it. That'll allow you to train at higher or lower precision. The default, of course, is real 32. Okay, one other thing this is more speculative, of course, is to offer the ability to train with AWS Link. And AWS Link is currently a very useful package. It's built into Mathematica. It's not documented at the moment, but it may be in the future. And it allows you to kind of interface with Amazon's AWS Cloud Compute services, I should say. And the basic idea is that you'll be able to use a very similar kind of interface to what you would do to do training locally, but you'll be able to point it at data that's living in the cloud in an S3 bucket, for example, and an instance that you've spun up, and that this training will then happen kind of independent from your session in the cloud, communicated over a channel. We have this new channel framework that will unlock that. You can sort of observe it training without having to remain connected to it in any way. And that might be quite a nice sort of usability and scalability improvement. And another thing that's actually quite connected to this particular feature would be to ensure that you can resume training from where you left off if the training gets interrupted for whatever reason. You can kind of do this now, but a certain amount of ephemeral state is lost, state that lives in the optimizers. So things like SGD and Atom maintain special, optimizers maintain special states, and if you stop them and throw away, if you stop net training and start it again, that state has to kind of like resynchronize itself, and that can change the results. So we want to make it that you can resume exactly from where you left off. And the place that this would come particularly handy with respect to AWS Link is if you're using so-called spot instances, which is it's a feature of Amazon's infrastructure that lets you rent rent compute hardware much more cheaply than you would if you would use the kind of more normal services. The downside is that your instances can be terminated at any time if the price that you're offering goes below the market rate. And so if that termination happens, you want to make sure that you can start it again and not have lost all of your progress, or at least not affect the results too much. So next, moving on to ergonomics. This is the thing that I'm particularly excited about. NetGraph, which Sebastian described in some detail, is great, but I don't think it's a particularly intuitive way to build computational graphs. It does have some advantages, which is once you've built this graph, it's actually quite straightforward to look at it and see what it does sort of visually. And you can, of course, drill down into the different pieces to see what's going on in those pieces. And that's quite nice. That's not something you can do with networks that are defined in other frameworks, at least as easily and straightforwardly as you can here. But the downside is that things that are conceptually quite simple can be quite kind of tedious to express in this kind of graphical way here, where you're defining individual vertices that correspond to operations and then edges that connect up to operations. And it's kind of like you having to compile, instead of sort of technical computer science jargon way of describing it, is you having to take some code and do the translation to static single assignment form yourself, and that's not ideal. It's served us well so far, but we think we can do better, and certainly other frameworks do better. And the way that we would do better is by making it appear that you're writing ordinary Mathematica code. And then we would translate this code into something very similar to the graph that you see here. So the underlying idea that I'm showing here, which is root mean square difference between two tensors, you can certainly express it with a net graph, but it's clearer if you just write the code directly that does the difference, the mean, and then the square. I think I left off power of 2 here, but that's not important for the example. This is the function. This is this feature that we call net function. Net function actually plays several different roles. One of them will be to make it easier to define net graphs initially, but it also will potentially have other roles that I'll talk about in a little bit. So very similar to that is the idea of custom layers. This is when, for whatever reason, the underlying framework, which is in our case is MXNet, but you don't really have to know that the underlying framework is incapable of expressing the computation that you need for your network. We hope that that's not often the case, but when it is, you might need to resort to coding something in C++ or C or Mathematica, and we want to make it possible to do that. But hopefully that won't come up as often and it won't come up very often. A feature that is also very important, and this is something that's much bigger than just the neural network framework, is the numeric array feature. And this is something that there's a sort of lot of discussion going on in the company right now to sort of make this happen for the next version of Mathematica. Basically, we wanted to make dense numeric arrays of arbitrary rank a sort of first level part of the language, first class part of the language. And that means that the approach we've been using so far, which is that kind of lists of lists are ways that you express numeric matrices, will somewhat be superseded by a new construct called numeric array. And numeric array will allow you to kind of guarantee that you've got efficient representation of potentially quite large numeric tensors, and easily see what their rank are. So currently, our list of lists scheme gives us the ability to get a lot of efficiency a lot of the time. So here's an example. Range will produce what appears to be an ordinary list, but underneath it is an efficient packed array, and you can see it takes 184 bytes to represent this array. But if you construct that list a different way, just by typing it in manually, it still behaves the same, but it's not actually a sort of contiguous chunk of memory. And that means that it's slower to do things like matrix, sort of linear algebra on it, and it's certainly larger in memory. You can see it's 280 versus 184 bytes. And numeric array will kind of do away with this distinction. You know, if a numeric array is there, then it's packed by definition. And we'll use these numeric arrays to represent the weights and the inputs and outputs of neural networks. Neural networks will be one of the kind of premier consumers of these numeric arrays in Mathematica 12, if all goes according to plan. One other important feature that I maybe didn't mention explicitly is that you'll be able to see the dimensions easily. That's not something that you can see for ordinary packed arrays, lists of lists. It's very hard to tell what this is, this object. But if it's kind of encapsulated in a numeric array, it's very straightforward to see. I'll have to probably skip over a little bit because how am I doing for time? Is it a hard limit at 8:30, or can I talk for a bit longer?
You can talk for a bit longer.
Great, cool. So flexibility, of course, as I mentioned earlier, that's the ability of our framework to model new and interesting techniques as they come up. And there's certainly some kinds of networks that we can't directly model today. And we hope to plug most of that gap by just introducing the appropriate layers, which don't yet exist. Some of these layers are essential, things like extract layer and argmax layer. Those look up particular positions in a tensor using another tensor. And this one produces positions of the maximum components of a tensor. These things, you can't do them any other way at the moment, but there are the layers that we think should exist just because they're kind of somewhat tedious to implement as net graphs. That's certainly part of the flexibility picture. Another important part is making sure that our higher order sort of functional style operators become more flexible. So netmap operator is one of these. It's a crucial one. And what it basically does is it takes another layer or subnetwork and applies it repeatedly to a higher rank tensor. So for example, if we have a linear layer that operates on, let me just use an example, it operates on vectors and produces vectors. You can see it operates on a vector of size 3 and produces a vector of size 3. Then a net map operator of that linear layer will operate on a matrix that's n by 3 and produces a matrix that's n by 3. And it just does that by repeating this operation on each of the n sort of rows of that matrix. That's very useful. It's used all over the place, especially in domains that have some notion of time, like audio or NLP, text processing. But where this falls down a bit is that we can't, I'm sorry, just going to close that quickly. Where this falls down a bit is that if you have a layer that has more than one input, then you can't put it in a netmap operator. So we want to fix that. And ideally, netmap operator will just look at the input and see the different, look at the network you gave it, see the different inputs, and it'll produce a higher order network that just naturally adds an n to all of the dimensions of the inputs and outputs of that layer that you gave it. And it'll in fact be a little bit more flexible than that. So you can choose to broadcast some of those and map others. There's a very similar story for netfold operator. This alone will be kind of unlock a whole family of different kinds of network that we can't currently express. Let me skip the dynamic evaluation thing because I think those who know what that is will sort of know immediately, and there's not much time left to explain it. Let me talk about the last major sort of future feature that we think is super important for the future of our framework, and that is interoperating with other frameworks. And for the purposes of that, we already do offer something. We offer the MXNet format. So you can open this page here, and you'll see this is a format we've had since one version ago. This lets you import and export from MXNet's file-based format, which is a mixture of two different files, a JSON file that stores the network topology and a params file that stores the weights. There are things that aren't ideal about that, though. It's quite low level. It's quite a lot more low level than our framework. And that has various implications. It means that it's very hard to import certain kinds of complex net because by the time they've been expressed in MXNet, they kind of, all the little components that you use to build something like an LSTM, it's very hard to recognize those and put them back together into an LSTM. So we can't import certain kinds of net, or at least if we do import them, they won't be very useful. You can export them, of course, but then sort of similar problem happens, which is that whoever's using your network, they're kind of stuck with various choices that you made. So if you're exporting a sequence network like an LSTM and it operates in a specific size, specific length, then whoever receives that network will only ever be able to operate on that length. They don't have a variable length representation of the original network. So the solution that we see at the moment, the kind of most promising one, is a format called ONNX or ONNX. It's a format that's supported by a variety of other frameworks. You can see here. There are also converters that convert between frameworks that don't directly support it. These converters aren't necessarily completely fully featured, but they certainly do support some serious use cases like image processing. And most importantly, there are a variety of device manufacturers that want to introduce hardware platforms or add driver support for their existing hardware that will natively understand the Onyx format. And that means that, while at the moment you can't target training on AMD cards, Onyx provides the possibility that in future you might be able to export a net from the Wolfram language and then train it in some form using tools provided by AMD. And also to do things like run nets that you've trained on in the Wolfram language efficiently on mobile platforms that run on chips like ARM and so on. So yeah, that's a kind of summary of where we want to go in the future. There's a lot here. We may not get to all of it, but we're also very keen to hear from you which of these features are you most excited about or most interested in. Let me maybe end that there. I think we will be around to answer questions, but I'm not 100% sure about that.
Yes, we will. We're gonna conclude the live presentations for this. We hope everyone enjoyed the talks and learned about concepts and tools that you'll find useful in creating your own neural network models. We will be sending an email to everyone in today's audience with a link to the webinar recording as well as notebook links. We look forward to seeing you all on May 9th for the second webinar in this series. That's when our topic will be image processing with deep neural nets. We will send out a reminder about this session as well. I would also just want to point out that we have a data science webinar series that starts 1 week from today. We'll put a link in the chat here. That link will also be found on the Wolfram U website and included in the webinar survey that will appear immediately following the session. We do appreciate your feedback, and we use the survey results to guide us in making improvements in the Wolfram technology stack and adding the features most important to our user community. All right, we'll keep it open for a few more minutes so that Tally and Sebastian can answer questions in the chat pane, unless either one of you want to mic up for another minute or so. Other than that, thank you guys again for coming, and we'll see you next time.